Hello fellow problem solvers. So today we're going to be doing IMO 2022 problem number 3, a number theory, in fact an actual number theory problem, yes, that we're going to be doing. And I suggest you try this problem out for a minimum of 45, 60 minutes, ideally anywhere between 120 and 150 minutes, not more than 270. If you'd like to go along with us, give this a go for the next 15 minutes. And what is the first thing you do in this problem? So you read this problem statement and you go, wait, oh, okay, there's a circle, there's some primes. The neighbors I multiplied together, I get x squared plus x plus k for fixed k. The k is always fixed no matter what's on the circle. And I must show that if I have this k and I have then this set of some primes, that there's a unique way to pair this up. Okay, that's what the problem is saying. But let's, at most one way that we can put these elements, so it's either we can't put them or we can. Well, let's see, like what would we like to pick first? S or K? That's a thing to think about. But how do you even begin such a problem like a difficult number 3 problem? And the answer is our heuristic that we use all the time, and that is play. We play around with the problem. And here we're going to play around with what? K, that's one option, if you feel comfortable playing around different Ks. But for me, I'd much feel more comfortable playing around with the number of integers that are in S, number of primes in S. So let's see what happens if the size of S is 3. And here, there's also a different level of, how should I say this, maybe complexity that you want to take this, or abstraction you want to take this at. I am pretty comfortable with just writing down, looking at, say, 3, 5, 7. Can they be on a circle together such that this is true? But if there is more complexity here, what I would do, if I had more trouble with this, I'd just draw a table of what's called PQ, and then the product being P times Q. 3, 5, 7, 11, 13, 17, 19, and all the way down here as one. And I'd write down all these products, and then I'd try to match them up. So that would be my, actually, start from 15 and 21. But for me, I feel okay with this level of complexity to begin with. So, it's a matter of taste, and you want to start off with maybe a little bit of complexity you can deal with, and then see, okay, I'm gonna just draw this table. Now let's go back to 3. So let me just first clean this thing up. What we have is, okay, this is now going to 15 is going to be x squared plus x plus k. We have 21 is y squared plus y plus k, and this is 35 is z squared plus z plus k. And we must find the appropriate x, y, z, and k. Okay. Let's see how we would be able to do that. Like we have 4 unknowns, 3 equations, we're an integer, so maybe we can't do that, but we should generally be able to come up with something. So let's see, can we do that? How do we even begin? Like we can maybe try for the small numbers, x can be 1, 2, 3, and that can give us a specific k, but this will not generalize too well to other cases, right? This will not build up nicely. So I want to also think about something that we can build up instead of 3, 5, 7, 5, just like 7, 13, and 3. Like I'd still, actually, let's say 7, 13, and 5. Like I'd still have a little bit of an issue and I need to work out with a lot more things for 35. So let me try to deal with the cases in a different manner, because I want to, play around in the long haul. If I have 7, 11, 13, for example, I'm playing around with that, I have at least 77. So let's try to see if there's something else. Okay, so these are, they're the same, but with different variables, all these equations. So what do I do in these types of cases? I personally, you add, you subtract, like these you subtract because there's some symmetry going on here. So for example, we have 35 minus 15 is 20, and that is equal to this minus this, so that is factors as z minus x times z plus x plus 1. Okay, so now this is either going to be 1 times 20, 2 times 10, or 4 times 5. 4 times 5 is unlikely to make x equaling 0. Well, you know, I think I want to play with it right now. So let's look at maybe one at a time here. So if this is 1 and 20, first of all, they can't be of the same, they are of different parities. So this thing is off. So it's either 1, so it must be 1 and 20, right? I mean, we can check the 4 and 5 just to be on the safe side, but let's go with 1 and 20, and we have, okay, z is, so 2z plus 1 is equal to 21, so z is equal to 10. Okay, but then k becomes negative. I mean, okay, let's roll with k becomes negative, just see what happens. We're just like playing around at this point. And then, you know, x is also then equal to, so because this is 10, that means x is equal to 9. Yeah, this is exciting, but kind of unlikely at this point is what I'm thinking. So what is my k? My k is equal to what? So this becomes 110 minus 35. Negative k is negative this. So this is 85. So k is equal to negative 85. And that gives me that y squared plus y is equal to 21 plus 85. And 21 plus 85, this gives me 106. I don't think I can factor this as y times y plus 1. So this shenanigans just fail. And we're trying to see, like, just playing around with it, seeing what's happening to it. If we take a 4 and 5, yes, okay, x will be 0. Z will be equal to 5. My question is, like, you know, which pairs can we even, under any circumstances at this point, just make them integers at the minimum? I'll even take a negative k. But under circumstances, can I even do something? So here I have x is 0, z is 5. And what does that give me? That gives me, well, that gives me k is equal to 15. And then here I have y squared. Okay, I have y is equal to 3, which seems to kind of work. I mean, everything is satisfied. There's triplet. Who knows? But, like, let's maybe, you know, play a bit more. So let's say it's 3, 5, and 11. Now I have 33, 15, and 55. Okay, so again, now this is x squared plus x plus k is 15. Y squared plus y plus k is 33, so this is 15. And we have that z squared plus z plus k is equal to 55. You know, 5 times 11, so on and so forth. Or no, maybe just one, okay, 5 times 3, this is 3 times 11, and this is 5 times 11. And now, what do you want to do here? Well, okay, let's, you know, play with this. So you want to get x, y, z, k, you know, subtract, sum two of them. Say we subtract these, what's it called? Say the smallest two. What happens then is we get, again, y minus x times x plus y plus 1 is going to be 3 times 6. And now we have some casework to deal with here, but the only thing we really can get here is a 9 times 2, I want to say, or well, we could also get 3 times 6. Parity issues. Now, if we were to get, say, a 9, okay, but I'm also doing this arbitrarily. Let me just look at all the other pairs that I can, you know, subtract. So what do? I get, okay, say this minus this, I'll get z minus x times x plus z plus 1 is going to be equal to 5 times 8. Okay, now this one has more casework than this one, because this one only has, actually no, this one has less casework. I was wrong. This one has only casework, that is, I thought because of about at a bigger power of 2, that means more casework, but it doesn't. So less casework. This one has to be 5 and this one then 8 because of this parity thing. The parity thing might come in useful later on. Like z times k must be odd because this is even. The product is odd. So like maybe there's something to do with the parity of these numbers, x, y, and z. And let's look at the final one would be if I did 55 minus 33, and that would give me z minus y times z plus y plus 1 is equal to, I take the 11 out. Okay, 11 times 2. Again, I just have one case here, and that is that this is 11 and this is 2. Now, which one do I want to like? Either one of these two cases are much better for me to deal with than looking at this case. Maybe it's this should be something about the smallest one that's making this happen. The smallest numbers, maybe. We don't know yet. We're just, trying to conjecture. Let's say take this case, and we have, okay, 2z plus 1 is equal to 13. That means z is equal to 6, and y is then equal to 4. Yep, all is good. What's it called? So z is 6, y is 4. What does that make? X, well, we can find it here, because z minus x is 5. That means x is equal to 1. And now what do we have? X squared plus x plus k is 15. So k is equal to 13. And this is in fact the only way we can form these numbers. So now, okay, it seems like there's, given at least 3 primes, like one equation gives us 2 of these numbers. I mean, maybe it's too early to generalize. Maybe let's take some bigger prime numbers. Say instead of 3, 5, and 7, let's clear up this part of the board and take 11, 17, and 31. And now we're working with some big guns. Again, this is a matter of comfort. You can still play around with some smaller cases, but now I want to just see what happens. Like, how would I do this in general? I have x plus x squared plus k is, say, this is my x, this is my y squared plus y plus k, x squared plus x plus k, and z squared plus z plus k. Okay, so this is 11 times 31. Y squared plus y plus k is 11 times 17, and z squared plus z plus k is equal to 17 times 31. Now, okay, let's subtract 31 and 17. So I have this is 31 times 6 is, actually no, this is not 17. I have 17 times 31 minus 11 is 20. This is going to be a lot of factors. This one isn't going to work. So this biggest one and the smallest one, when I combine them together, I have a decent shot at this not giving me something nice. This is now z minus y times z plus y plus 1. Why is that not nice? I mean, this has a 5, and I now have a couple of cases. I have a 5 on this side with evenness, and I can have even things on this side. So this is in 4 times 17. I can have 10, and 2 times, and not 2 times, I have 20. I can have 17 and 20 here. Oh, actually, it's not so bad. Oh, I can also have a 1 and 5 times 4 times 17. So it's not looking super duper good. For me, this z plus x plus y doesn't look nice, doesn't look great. So let's maybe, try to see if I take z minus x, or maybe I'm not seeing something and you're seeing something. Again, you should feel free to pause at any point in this video if you feel like, oh, I'm getting an idea. This is now 31 times 17 minus 11 times 6. Okay. 31 times 6. Okay, I know there's going to be a 31 is going to be on this side. So it's either 31 and 6, or it's 93 and 2. Like this 31 sort of, I have a size argument, so that can help me know where this big prime is. Can I have, if I had, so let's take the 2 and 93 first. I would have z is equal to 2z plus 1 is 95, so 2z is 94. Actually 94 divided by 2, z is equal to 47, but that's, no, z squared is then bigger than 31. This is just then k is negative. Then, I mean, like, is this, like, should I pay attention to that? Like, maybe I should pay attention to that. Like, these are the naturals. So this just does not work out because it's too big. And now, okay, with 31, I get that z plus x, actually I get 2z is equal to 31 plus 6 minus 1, so that is 36. Z is equal to 18, okay, it's between the two, that's okay. And now z is 18, x is then equal to, so I need to get a 6, so x is equal to 12. And now, okay, I have 18, 12 for x. Might this solve for me this case? No, 18, y could still be a lot of things. Like, y is the smallest one. I mean, it has to be less than 10, less than 12. So z minus y is at least 8. So I know it's this now. So I know it's probably going to be around, y is 1? Huh. Let's actually, let's see if this actually works out. So after we do the calculations with k, we get that k is equal to 185, z is 18, y is 1, x is 12, ends up working out. Now, and it seems as we play with other prime numbers, the triplets end up working out, but it's not just that they're working out. What's important for us is how we're finding them, right? We need to take care of even the little details, because that will give us a sense for what to do in the big problem. There was a size argument to be made for this number that got us to deal with the cases very quickly. Now, what is it like? This is 31, so we were taking a number that's, maybe it's the fact that it's much bigger than these is the problem. Maybe we had a 29 here and a 23 there, it would be a different story, but we should test that out, test out a hypothesis for that. Or we can go to P, Q, and R and see if there's something that we can find in general from here. And now I invite you, pause for the next 10 minutes and play around with other maybe numbers of free, or take PQR's, free prime numbers and see if we can always, because right now we're playing around, we're getting, okay, sure, in some cases we get a 0 for one of the x's instead of getting something that is a positive integer, but still we're succeeding no matter what we play around with. So, like, I mean, almost succeeding, right? Like, not quite succeeding, but we're there. Maybe that's even a thing that the problem is like asking us to do, generalize to more numbers of this form. Like, if it works for the non-negative integers, it works for the positives as well, for x. Maybe that's the thing. Like, maybe we need to do a slight generalization, but who knows at this point? Like, it seems to be working in general. Let's at least see when is it that it fails, and when is it perhaps that we get one of them is 0. And this is all that we get through much more play than I'm showing here on the board for the sake of our time. And now, with the play, we move on to general PQR, and we get that once I have, say, P, Q, and R, and say that, P is bigger than R, it's bigger than Q. What I have is, if I've updated this as x squared plus x plus k, This is y squared plus y plus k, and z squared plus z plus k. What we did previously was we said, okay, let me subtract this one from this one, and I'll get, okay, x minus y times x plus y plus 1 is equal to r minus q times rp. And we saw that even if we were playing around with r minus q to have a lot of factors, the fact that it's a p, like there's a size argument to be made about x here. Now what is this size about this x plus y? So can we make this size argument here? So x is bigger than y. Okay, we're good with that. But now, can this be at least 2p? Well, if this was at least 2p, then we would have x would be at least around p, right? This would be at least p, this would be at least p minus 1. Like that's the smallest they can get. Like x would be at least p. But then I have x squared plus x plus k is equal to p times r. This would be bigger than p squared in that case, which is not the case. So if I have like a p that's bigger than both of these, then I know this is going to be p and this is going to be r minus q. And now I can find out what x and y are, right? Now I have 2x plus 1 is equal to p plus r minus q, and 2y plus 1, I want to subtract this, is equal to p plus q minus r. Okay, that's oddly symmetric. And this also gives us our k. Like this thing can give us, like now I have x squared plus x plus k is equal to, in fact, p plus r minus q squared plus p plus r minus q plus k is now equal to p times r. And from here, I have directly what k is equal to. So from here, what do I have? I have a p plus r minus q. Oh, p plus r minus q. I need to have a minus 1 and then over 2. I need to have a minus 1 and then over 2. Okay, so it's a bit ugly, it seems. K itself, not the most beautiful type of answer. Maybe there's something to be done about x times x plus 1. Could it be a difference of squares? Potentially, if I'm thinking x is equal to some s minus 1 over 2, where s is equal to this, whatever, let's call this s. Then I have x plus 1 is s plus 1 over 2. So x times x plus 1 is s squared minus 1 over 4. Okay, so that's doable-ish. So I have, in fact, k plus this now s squared, so plus p, actually I can just put this, all of this on the other side. I have k is equal to pr minus this s squared, so minus this, let me 4pr minus s squared plus 1 over 4. And now what is this 4pr minus s squared? This 4pr minus s squared turns into, so I have p, so I'll have what? I'll have minus 2qr minus 2pq plus 2pr. So it's this minus that. So in fact, I'll have that k is equal to, divide by 4, 2pq plus 2pr plus 2rq minus p squared minus q squared minus r squared plus 1. Okay, so this is what I get as my k by playing around with these free numbers. And now my question for you is, what are these? Like, what is this telling you about K? That's actually quite surprising. For me, this is saying K is symmetric within P, Q, and R, which is kind of unexpected to me. I mean, this means, like, if so, now by the same token, if this is the case, I should be expecting to get 2z plus 1 equals R plus Q minus P. Like, this is what I'm expecting to get because I have this symmetry. And in fact, if I plug this K into this equation, that is what I will get. Now I invite you here to pause for 10 minutes and ask yourself, what is it that we really used here? And try to see, like, okay, now that we have this general solution for free numbers, just playing around with K equals, with the size of S equaling 3, and finding we can always almost conjure up a K and an X. I mean, the problem here is when this thing is equal to 1. When P plus R minus Q is 1, or another way, I think it's here where the problem is, where R plus Q is equal to P plus 1. Because if this is equal to 1, then Z is 0. And that is the only place where we have a 0. So if that is where the issue is, what can we do about that? Now, do we care about that? Like, is it not important that these numbers are positive? Like, what happens if we include a 0? Another thing to think about as we're going through this, x squared plus x plus k, like, these are two, and this is to have x squared plus x congruent to minus k modulo p and modulo r. This is a modular arithmetic with a quadratic polynomial. This can have at most 2 solutions because it's quadratic. That's also a different way of thinking about what these things are, a different perspective, if you would, on the problem. The perspective would be, okay, x squared plus x plus k is, so both x and y are smaller than p, otherwise we'd get this insane contradiction. And x and y, they are different solutions to this equation. X squared plus x is congruent to minus k. So if there are different solutions to this equation, when I subtract them, they can't be identical. So, and these x and y are between 1 and p minus 1. So I have, and when I subtract them, I'll get x plus y plus 1 is equal to p, which is what I had here in a different manner, right? I was saying there are these size constraints that I have on x and y, and this is why this is equal to p. And here I'll just say this before we continue onwards. This part over here, if you had had this is definitely a point. Probably 2 points, because you're talking about things in the problem that are leading towards a solution. Like, you're taking this triplet now, and you're looking at it, you're seeing what happens to it. And this is, mind you, from play. Figuring this part out, that this is now P. If I have, and now the next sort of thing to see is, this is P, not because I have 3 elements here. It is P because this is equal to P because P is bigger than Q and R. P is bigger than its neighbors. I've not used the fact that Q and R are neighbors as well at all to get to P. And I've not used this fact at all to get to what my Z is. And here, with that, you have 3 points. And here I invite you to pause for the next 10 to 20 minutes, move on to s equals 4, or maybe even generalize, whatever you feel like. And here's the board now cleared up. So what we have, once we clear up the board, is, okay, if we're looking at, say, 4 members, say we have P, Q, R, and S, say they're all primes. So I have, okay, let's say P is bigger than Q, and okay, let's say S is bigger than P, so that we don't have this, but then let's say, okay, R is bigger than S, but then R is bigger than Q. So we can find one such that the two of its neighbors are smaller, and say, okay, that is R is bigger than S, and S is bigger than Q. Okay, say this is x squared plus x plus k, and this is y squared plus y plus k, okay? So I have y minus x times y plus x plus 1 is equal to r times s minus q. Okay, r is a prime number. I also have this is equal to rq, which is less than r squared, which is strictly less than r squared plus r plus k. And so x, or actually maybe this is just bigger than x squared, so x squared, or even greater than or equal to, if I'm including my 0, then x squared is smaller than r, so x is smaller than r, and similarly y is smaller than r. So this thing over here must be divisible by r. X is greater or equal to 0, and so is y. We're playing around with that 0 introduced with them, just to like get rid of that edge case. And so x and y are different, right? That's also a thing. X is different from y. And now x plus y plus 1, so x plus y is now less than or equal to r minus 1 plus r minus 1. So let's add a 1 here, plus 1, which is less than 2 times r. So this is also bigger than 1. And that means this here is in fact equal to r, which makes y minus x equal to s minus q. And now what do I get? Well, I get that y is equal to r plus s minus q, and now this minus 1 divided by 2, and x is equal to the opposite, r plus, actually it's, yes, r plus q minus s minus 1 over 2. And what is my k? Well, my k, mind you, from the thing we found previously, just by finding one of the y and x, we have the k. And then k is equal to 2sr plus 2sq plus 2rq minus r squared minus q squared minus s squared. And then it was a plus or minus 1, I forgot actually. So the 1 is, so it's s squared minus 1, so it's like that. S squared minus 1 over 4 that I have. Okay, it's all of this over 4. So it's that minus 1 in the s squared. When I move it to that side, it becomes a plus 1. I completely forgot, and I don't want to do calculations again. So this is now, what's it called? Call this t times, what's it called? So this is t squared minus 1 over 4 plus k is equal to, what is this now? This is for y. So for y, we have this as sr. In other words, k is equal to 4sr plus 1 minus t squared over 4. So it's a plus 1 at the end here. And now what do I do? Pause for 5 to 10 minutes. And the answer is, well, I have what k is. And I have now, okay, r and s are neighbors. Q and r are neighbors. And sure, the same thing also holds for p. What do I also know? And this is the big idea. I know for S and Q, there exists an Z such that Z squared plus Z plus this K is equal to S times Q. And what am I going to show that Z is? I'm going to say that for Z equal to, so I had an R plus S and R plus Q. So now it's going to be a Q plus S minus R. Q plus S minus R minus 1 over 2. If I take this Z with the K, I get what? I'll get Z squared plus Z plus K is equal to S times Q. And this thing over here is a integer because these are integers. These are all primes. And so now, what can I do? Well, in general, now I know, okay, R is the biggest one here. And in saying this one ordering, you know, the Q and S are next to it. Like this, uniquely, the K, like there's nothing to reorder actually here, is the thing. But say I had another thing here. Say I had a prime T and a prime V here as well. So I didn't have 4, I had 6 primes. Now sure, or actually no, say I had 5. Let's take it one step at a time. Now the question is, could I switch T and P? Well, think about this. This problem condition now holds for this specific K. We have also a unique P. Like we can think about these two as being their own. When we had the 4 primes, let me do it like this. When we had the 4 primes, we had this whole thing. These were on the circle, okay, with our K. Now, can we switch it up? Is the question. But I can ignore sort of R, and I'm thinking about these 3. They also satisfy the relationship that the K satisfies the same relationship here. Like it's as if we had these 3 numbers on a circle. And these 3 numbers also give us this unique K. So just looking at the biggest one, R, and its 2 neighbors, gives us a unique K. But then when we forget about the R, when we look at these 3, we also get that unique K. And we know that we still have the same uniqueness here. And with this idea, I invite you to try to bring together the problem and try to generalize it for all n. And I'm going to clear up the board and do just that. So, till this point, we have, if you haven't figured out the ending now, we have 6 out of 7 points by the marking scheme. And also, mind you, if we just had the 1 or 2 points, just by figuring out this x plus y plus 1 is p or r, like whichever thing we used, like that would also give us 2 points. Right, so up 29 was the cutoff for silver. Say you solve the other 4 problems, like 1, 4, 2, 5, that would give you a silver. And say you're getting this far off, then 34 was the cutoff for gold. So if you get this far, you basically solve the problem, you get a gold medal. But I want to just point out, you want to even write down banalities. Like there's even a part in the marking scheme which says, if you claim something, one part of the solution, and you don't prove it, like you can still get a point. Okay, so these like little points at the end, especially when you're going for the gold, it matters. So now let us continue onwards with our problem. what is the basic thing? So if S is smaller than or equal to 3, then if it's equal to 3, there's nothing to prove really, right? There's nothing to prove in this case. So let's assume we've done this for some S that's equal to N of this size. We've proved uniqueness given a K and the size of any, of any N primes. So now let's take S that's of size N plus 1. And what are we going to take? Well, let's take the biggest prime here. Let's say that's P. Its neighbors are Q and R. We know that Q and R, that if I take out P and just focus on S with a difference of P, I'll get a smaller set, okay? And this smaller set has what? It has a unique order, right? The ordering with this set is unique. And now what holds true for like this P? Well, I need to have my X and Y such that X plus Y plus 1 is equal to P. And I'll have that X times X plus 1 is congruent to minus K modulo P. But mind you, X and Y here are two unique pairs. Like K is already given. X and Y are the unique pairs. So without P, this has a unique ordering. And Q and R, and given this K, given our K, without P, this has that same unique ordering. Because we saw that with P previously that R and Q, there will also be a Z such that Z squared plus Z plus K is equal to R times Q. And now, okay, so without P, we have this. These two solutions are unique. But these solutions, this X squared plus X plus K, needs to equal not just, it's P times something, but that is P times R, and Y squared plus Y plus K needs to be equal to P times Q. So the neighbors of P are also uniquely defined. Mind you, if you just saw this, which is a direct consequence of the thing we found before, that is total of 3 points. Take 3 points on this problem number 6, and you've got yourself a gold. And that's why I'm also just want to put this near the end, write stuff down. I always say that I didn't do that at certain points, and it's important that can be really helpful. So with this in mind, we have that this ordering here, if without P, is unique. And if I'm adding a P, its neighbors have to be Q and R. And so there's no way I can order them in some other way. If I could, P would need to go somewhere like else. If Q and R have to be its neighbors, so it has to be tied to the two of them. But then if I remove P, if I have a different ordering, then I would have a different ordering for the set S without P, which is of size N. By my inductive hypothesis, I can't have that. So this finishes up our problem. And it's a really big number theory problem. Like there's not much, like there's some combinatorics, I would say, in this problem, playing around with this, but fundamentally at its core, it's a number theory problem. And what really helps here is just, playing around with K equals 3 and seeing, okay, I am almost always getting that not K equals 3, the size of S equals 3. And you see that you're almost always solving, but the places where you're not solving, you're getting a 0. And you could generalize, right, to the non-negatives. And we have effectively done that. We've generalized to calling these numbers, say, if they're paired up, if there exists a non-negative Z. And if there's a pairing with the non-negatives, then there's ones with the positives as well. But the main focus still is, okay, we played around with some primes and we saw, okay, we could determine actually what these X and Y were and the order in which we determined them. To make it always the case that we can determine them was we first looked at, okay, the biggest one and its two neighbors. Like we looked at that, these two products, subtracted them, and then found out, okay, has to be this biggest prime of the free. And from there you see, okay, what am I using? Like that's the question you want to ask yourself. Whenever you're coming up with something through play, like what are the real things that I'm using? Am I using something specific about R minus Q? No, I'm actually using something about only the size of P. Now that's generalizable. The factors of R minus Q, that's not generalizable. Even though there's a 2 there, you know nothing else about those factors. So that is the idea. You build up slowly to get to, okay, so that is what determines my K. And I even have what K is. But if I've only used these, if I haven't used this fact at all, and I've gotten as a conclusion that there's a Z for this, I can generalize this idea to numbers that are on a circle. One that's the biggest one has 2 neighbors, or smaller than that. It defines what K is. These 2 small neighbors, like smaller neighbors, they define what K is. And it also connects these 2 small neighbors as if this one wasn't here. So that is the sequence of steps sort of that we do toward this reasoning. It's by no means an easy problem. I wouldn't say it's easy. It's a good, like maybe a medium-ish hard problem, of the harder ones, but fantastic in my point of view. That it's also just a pure number theory, like we're using some of these quadratic residues, or actually quadratic polynomials modulo P, to know things about the solutions. Like you might see that immediately if you see like what X is, like it's a solution to X squared plus X is K. There can be at most 2 of those. Right, so then there's like something to be done there. But this finishes up this lovely problem, and as always, thanks for problem solving.